In the last lecture, what we looked at was lift-dependent drag, and in this lecture we're going to look at the other type, the lift-independent drag. And our lift-independent drag has four forms. We have skin friction drag, interference drag, trim drag, and form drag, and we'll look at these in turn. Form or pressure drag is what we find on any bluff object. Bluff objects, circles, spheres, anything that isn't a streamlined or airfoil shape. And what we find on these types of shapes is that the flow doesn't remain attached. It tends to separate quite early, and we get these large turbulent separated wakes. And inside that large turbulent separated wake we'll have a low pressure. Now on the front we've got a stagnation point, which is a high pressure, and on the back we have a low pressure. So we've got a pressure difference, so that object is going to be sucked backwards, and that sucking backwards is drag. So our pressure drag is, as it says, a pressure difference causing a drag force on an object. Now pressure drag can be huge, because if we look at two objects which have the same pressure drag, this little circle and this airfoil shape, we see that something about 100 times bigger and streamlined will have about the same drag as a bluff object of 1/100th the area. So streamlining reduces pressure drag a lot. The one time we'll get high pressure drag from an airfoil is when it's stalled. So here we have the airfoil above the stall angle, and we can see that once the airfoil is stalled we get a large separated wake behind the airfoil, and therefore high pressure drag. What you find when you stall an airfoil or stall an aircraft is that the rate of descent goes up. And what you're seeing is, okay, a small decrease in the amount of lift because the airfoil is stalled, but predominantly you're seeing a large increase in drag, and therefore a reduction in the lift to drag ratio, and therefore a much higher rate of sink. And so we design aircraft nowadays without bluff objects attached to them, if at all possible, to increase their performance. Now, the other predominant form of drag is skin friction drag, or the drag due to the presence of the boundary layer. Now when we look at drag, this skin friction drag dominates at high speed, because parasite or lift independent drag dominates at high speed, and lift dependent or induced drag dominates at low speed, and the sum of the two gives the total drag of our aircraft. So skin friction drag is the drag that we really worry about when we go up to high speed. So why does the boundary layer generate a drag force? Well, it's because of Newton again, third law. For every action there is an equal and opposite reaction. In a boundary layer, the fluid is slowed down from the free stream velocity to 0 at the wall, and therefore we must apply a force on the fluid to slow it down. From Newton, therefore, if we apply a force to the fluid to slow it down, the fluid applies a force to us, which is drag, which tries to slow us down. So that's where our skin friction is coming from, due to us slowing the fluid down through the boundary layer. Now boundary layers exhibit a fluid flow phenomenon which we find in most flows. Most flows will start off nice and smooth and laminar, as in this water coming from a tap, but as we increase the velocity they will tend to turn from laminar to turbulent, which is what we see in this smoke coming off of this cigarette. Nice smooth laminar filament of smoke, and then becoming chaotic, random and turbulent. And boundary layers show this phenomenon. They tend to start off nice and smooth and laminar over the leading edge of the wing, and then become random and chaotic or turbulent as the flow transits from leading to trailing edge. And also, as we see here, nice laminar boundary layer to begin with in these kind of hydrogen bubble filaments, becoming random and chaotic and much thicker. Our turbulent boundary layer we see here is much thicker than our nice smooth laminar one. And if we calculate the skin friction drag coefficient for a laminar and a turbulent boundary layer, we come up with some interesting results. This is the K21, and we can do a sum and calculate the skin friction drag on the wings of a K21. And if we do this, what we find is that if the wings on a K21 were purely laminar, or the boundary layers on the wing were purely laminar, the drag would only be 15 newtons, around about, what's that, a couple of kilograms. However, If we had a fully turbulent boundary layer on the wings, then the drag force acting on our wings would be 58 newtons, almost 4 times as much. So a laminar boundary layer has about 1/4 the drag of a turbulent boundary layer. So obviously what we want to do is to have laminar boundary layers over as much of our glider as possible. Now how do we do this? Well, this is an old NACA 0012 12% thick symmetric airfoil from the National Advisory Committee for Aeronautics. And what we see on this plot is the velocity over the upper surface of the wing plotted. Now the velocity is inversely proportional to the pressure. So if the velocity goes up, the pressure goes down. And so over the front of this wing we can see that the pressure drops with distance over about the first 10% chord. Now when we looked at boundary layers, what we saw is that if the pressure drops with distance, then the boundary layer stays attached. But it also stays nice and thin, and it also tends to remain laminar. So in this region here we'll have a nice laminar boundary layer. When the velocity decreases and the pressure goes up, then we get the opposite effect. And what will happen is that the boundary layer will tend to turn from laminar to turbulent. And so we'll probably have a turbulent boundary layer over about 80% of the chord of that wing section. And so we see we've got quite a high drag coefficient of about 0.006. In the late 1930s, the engineers at the NACA said, well, what's happening here is that it's because the point of maximum thickness is at about 25% chord aft of the leading edge, which is giving us that most of our wing has an adverse pressure gradient and therefore turbulent boundary layer. And so they designed a new type of wing called the 6-digit series. And they moved the point of maximum thickness back to around about 60% chord. Now what we see is over most of that wing the flow is accelerating and therefore the pressure is dropping. So we've got a negative pressure gradient over about 60% chord of that wing, and we'll have a laminar boundary layer over about 60% chord of the wing. These were known as the laminar flow airfoils, and here it's a 12% thick wing, same as the one we saw before, but look at the drag. It's only about half of that previous old-fashioned 4-digit series wing. There is a slight problem with this, that when you look, that low drag only occurs over a limited lift coefficient range. It's known as the drag bucket. And that shows us the development of wings over the last 100 odd years. Clark Y was one of the first airfoils to be used, and that had laminar flow from about 5 to 20% of the chord length. 4-digit series still in use today on the likes of Cessnas, again 5 to 20% of the wing covered with a laminar flow. Or when we get to the 6-digit airfoils, which were on the P51 in the 1940s, we see that we've got about 60% laminar flow over those wings, and so therefore we've got a very low drag because most of our flow over those wing surfaces are laminar. And we see these wings being employed in gliders. Here's the old T21, Slingsby T21, the Zebra, or barge as it's well known. It has a NACA 4-digit series wing, 4412, 4% camber, 40% chord and 12% thickness chord ratio. And what we see there is that the parasite drag, the skin friction drag of that wing, was about 0.006. When laminar flow airfoils were implemented onto gliders, here we see a case 6 from Schleicher, we can see that the CD0 value has reduced down to about 0.005, and again over a limited lift coefficient range for that aircraft. But as long as we get that lift coefficient as the lift coefficient that we require in cruise, then we're fine. The problem was keeping these wing sections, or these laminar wing sections, is that in the 50s, 60s and early 70s the manufacturing techniques were not really up to generating the nice smooth shapes that were required for laminar flow sections. Here we have wing ribs with plywood over the leading edge and then fabric covered trailing edges. It was only really with the development of composite gliders from 1957 onwards, here with the Ackerflieg Stuttgart's Phoenix, which was the first composite or fiberglass glider, that we could get nice smooth surfaces whose shape could be very well controlled, that we actually get laminar flow over most of the wing. Now again, we have this problem that with a laminar flow wing we have only a limited range of lift coefficients over which we get the low drag coefficient. And so the way you get around this is by having trailing edge flaps. What we see here are the wing or the airfoil characteristics for the airfoil that's fitted to the Antares. It has a DU, which is Delft University 97 wing section. And what we see here is that depending on the lift coefficient we want to fly at, which is the speed we want to fly at, by deflecting the flaps we can generate the drag bucket over different lift coefficient ranges. So when we're flying slowly, we'd want to have a flap deflection of 10 degrees because we're flying at high lift coefficient, and therefore as we speed up we would change the flap setting in order to get my low drag coefficient at the CL at which I'm flying. Now we've gone into all this effort of creating these lovely smooth perfectly shaped airfoils which have laminar flow. The problem comes when they get dirty. If you let your nice laminar flow wing section get covered in dirt or bugs, if you scrape it, if you have untaped joints around your canopy, poor seals between the various different sections of the wing, what happens is that the roughness on the surface causes the boundary layer to transition from laminar to turbulent early. And what we see on this little smoke visualization of flow over a flat plate, where it initially starts off nice and laminar and then becomes turbulent, is that yep, we've got laminar flow here going back to around about 30% chord of that flat plate, but here the boundary layer is turbulent from the leading edge, and the reason for that is that there's dirt or roughness there, and dirt and roughness creates turbulence, and it does what's known as trip the boundary layer and turns it from laminar to turbulent early. And once it's transitioned from laminar to turbulent, you can't get it back to laminar. So look at a K21. Typically a lift to drag ratio of 34, but if we allow it to get dirty and get a 50% increase in the skin friction drag, our lift to drag ratio drops to around about 29. And the lift to drag ratio of 29 is the same as an old K13. So if you let your nice K21 get dirty, you might as well fly an old K13 instead. Trim drags the drag due to the presence of the tail plane. Normally in flight, our lift acts behind our centre of gravity and generates a nose down pitching moment. Now in order to counter that nose down pitching moment, our tail plane generates a download to pitch the nose up. Now the problem is that when we say that the lift equals our weight, it's not actually true, because the lift has to balance the weight but also the downforce from the tail plane. And so because we've got the tail plane generating the downforce, we need to generate more lift, and if we generate more lift we generate more induced drag, and so our trimming surface at the back there is generating more induced drag on the aircraft. Now how do we reduce trim drag? Well, one thing we do is we have a long tail arm. A moment is a force times a distance, and therefore we can reduce the force required on the tail plane by having a large distance over which that force acts. And so if you look at modern gliders, they have a very small tail plane compared to the gliders from the 1950s and 60s. The other thing we can do is we can put water ballast into the tail to get the centre of gravity in the right location, that the moment generated by the lift force is quite small, and therefore the tail forces need to be small as well. And here we see an aircraft smoking, i.e. dumping the water ballast at the end of the flight, such that they can land without the water ballast. And finally, interference drag. Interference drag is essentially the problem that when we join two surfaces together, such as the wing and the fuselage, or the tail plane and the fin, what happens is that the flows interfere with each other and cause the laminar flow to transition early to turbulent. And we can see that in wind tunnel pictures. These are wind tunnel pictures of an aircraft in a wind tunnel. It's covered with a fluorescent powder in oil. And what happens is when the flow's laminar, the oil and powder doesn't get scraped off the surface, but as soon as the flow transitions from laminar to turbulent, the turbulent flow scours the oil and the powder off the surface. Once you've run the wind tunnel, you turn all the lights off and turn on a UV light, and you can see the flow patterns because the powder's fluorescent. So what we see here is there's the wing, and we see that the flow is transitioned to turbulent upstream of the wing due to the presence of the wing. And if we look at the upper surface and the lower surface of the wing, we see that the presence of the fuselage has caused the boundary layer on the wing to transition from laminar to turbulent early. And so where we join surfaces together, we have to be very careful because they tend to cause transition in the boundary layer.